Welcome to another podcast. In this episode, we're going to be taking a look at what is called the harmonic motion equation, and specifically we're going to look at the case where we encounter simple harmonic motion. Now, as the name might imply, simple harmonic motion is the simplest explanation of oscillatory motion in mechanics, and we derive it from looking at the spring mass equation. So if you look at the spring mass equation from last time, recall that if we have an object with mass m and we are imposing a damping of c with a spring constant k, then in the case where we have an external force F, this governs the displacement from equilibrium y of the mass. I want to do a little bit of algebraic manipulation to this, starting by dividing everything through by m. So I'm going to divide through by the mass, and we obtain the following equation. And then I'm going to rename some things. I am going to call c over m 2p, and I'm going to call k over m omega naught squared. Now, I know that may seem weird, and I'm going to call f of x over m lowercase f. I know this may seem a little bit weird to call them these things, but there's a reason for it. So let me just quickly describe what that reason is. This is the harmonic motion equation. So if p is equal to 0, this equation describes simple harmonic motion. And if p is not equal to 0, then it describes what is called damped harmonic motion. And so we're going to be looking at both simple and damped. We're going to look at simple in this video and damped in a future video. But the thing I want to address right now is, why did we choose these specific values 2p and omega naught squared? And quite simply, those were chosen so that the quadratic formula will have nice roots. That's the only reason we did that. In fact, if you ever see a equation that has a twice the middle term and then the c term squared, that is done entirely because we're thinking about finding roots of that equation, and this makes the roots simpler to analyze. C over m is a constant, as well as 2p. K over m is a constant, as well as omega naught squared. So it is a very common practice in differential equations, as it is in all of mathematics, to reshape constants in forms that are the most usable for our purposes. And so we want to look at the simple harmonic motion equation. And so in the case where we have simple harmonic motion, the equation becomes, if p is 0, y double prime plus omega naught squared y equals, and I'm going to focus on the homogeneous case today. So we're looking at f of x being equal to 0, because at least as of right now we are focused on homogeneous second order linear differential equations. In order to solve this, we would find our characteristic roots. Characteristic roots come from the characteristic equation, which in this case is r squared plus omega naught squared equal to 0, which, if I do a little bit of solving here, I get r squared is minus omega naught squared, or r is the square root of minus omega naught squared. Now, what's interesting about this, and it should really be plus or minus here, so plus or minus that. What's interesting here is we want to pull out the negative, because what you notice here is, regardless of the value, because omega naught squared is a positive value, remember k is positive, k is greater than 0, and m is certainly greater than 0, which makes omega naught squared, makes that greater than 0. Because of that, this root is clearly going to be imaginary. So we're looking at plus or minus, the square root of negative 1 is I, and the square root of omega naught squared is omega naught. And so our roots in this case are purely imaginary, meaning that there is no real part. Because of that, if we use our what we've studied previously about linear equations, this means that the general solution y of x is going to be e to the real part, which is 0x, times c1 cosine of the imaginary part plus c2 sine of the imaginary part. Now I'm doing all this for effect because you can tell that this is going to simplify greatly. We have no real part, so we have no exponential in our solution, and we simply end up with a linear combination of cosine and sine with the same frequency. So let me talk about the names for some of these things. P is the damping constant, and the more important term for us is omega naught is the natural frequency. Why is it called the natural frequency? Well, you can see if we have no damping and we have no force, which means we start the spring moving and we don't affect it in any way other than to let the spring pull itself up and gravity push it down, we get that tug of war going, and those are the only factors involved. If those are the only factors involved, then the spring oscillates with a natural frequency of omega naught. You can see the frequency here is omega naught. And so what's important about this is we understand that the resulting solution in the case of simple harmonic motion is we wind up with a pure oscillation that has frequency omega naught, and it has period. Remember, the period p is 2 pi over the frequency, and it has amplitude given by the square root of c1 squared plus c2 squared, which means that the amplitude is affected by the initial conditions. So depending on where you start the spring, it's going to lead to an amplitude that's larger if you have a larger displacement to start with. If you imply a sharper force initially to the spring, meaning you impart a stronger initial first derivative to y, so if y prime is large in your initial condition, both of those will lead to larger amplitudes. And there's nothing to damp out the motion here, so this tug of war keeps going on forever. We're simply going to get, now that's not practical, but we're going to get this pure oscillation, which is a cosine or sine curve back and forth for all time. So there's one last thing to say here, and we've noted this on previous videos. Because this is a pure oscillation, I can write this in the form cosine omega naught x minus phi, where phi is the phase lag and a is this amplitude. And so we talked about how to do that in a previous video, but it is a linear combination of oscillations of the same frequency, which can always be written as a pure oscillation of that frequency with some appropriate lag. So this is what happens when you have no damping in the spring mass equation. It comes out to be what's called simple harmonic motion. So we're going to look at the damped case in the next video, and we're going to be applying these throughout the rest of the semester. Thank you for watching.